Let's see now how we can make best use of this analogy in order to solve this mystery. Now, if we want to think directly analogously, there's one very easy way, of course, we could set up this current I, right? We could simply take this wire of positive charge and get it moving with a certain velocity v here. So let me mark the velocity v off to the left. If we would do that, it would take these positive charges and definitely generate a leftward moving current. And the nice thing about this situation is that, in fact, all of the positive charges, if we were to move the wire rigidly, would be traveling with this same velocity v. In that particular case, when we do that, the question then is whether we can find a simple relationship between the velocity at which we set this charged wire in motion and the resulting magnetic field. So let's investigate those possible relationships. So we're hoping to find something that's related to the magnetic field by combining the velocity with which we're going to move our wire here. We're going to grab this whole wire, as I've just said. We're going to move it off to the left with this fixed velocity v. So we want to find some relationship between that velocity, the electric field, because this is something that we understand deeply how to calculate, and the magnetic field. So let's take a guess and see if we can guess at what that relationship must be. Well, certainly the magnetic field that I generate by putting this wire in motion is going to be proportional to the velocity. So I would expect that it depends upon the velocity v. I would also expect that if I make a wire with a larger density lambda, right, so that it has a larger electric field, I would expect that this electric field then, being larger, would contribute to a larger magnetic field as well. So I would expect then that the magnetic field I'm generating is also proportional to the electric field. Finally, I have to find some way to combine these two vectors, velocity and electric field, to produce the third vector, the magnetic field. So I need some kind of product that takes two vectors and gives me a vector. So just like we've done before, and as we constantly will see in the magnetic field case, the whole theory of magnetic fields is constantly riddled with these extra cross products appearing rather than ordinary products or dot products. So our guess is going to be that maybe if I do something like this, take the velocity at which I set this thing in motion, cross it with the electric field, that in that case I will generate something very closely related to my magnetic field. And my strategy then is that once I have that, I should be able to massage my result for this one particular case into a form that I hope will elucidate what the general form for the magnetic field must be. So let's see how well this works now. If I do V cross E, let's try to calculate what exactly I'm going to get in this case. So carrying through the cross product as usual, that would give me the magnitude of V, of course, times the magnitude of the electric field E, times the sine of the angle between them. In this case, at my point, remember, E is pointing straight upwards, whereas the velocity is directly off to the left. So upwards is this direction, to the left is this direction. That makes a nice, perfect right angle in here, of course. So that's times the sine of 90 degrees, which we like because we know the sine of 90 is 1. Finally, to determine the direction, we have V and E. It's V cross E. So once again, we orient our fingers along the direction of V. So our hand will be pointing off to the left in the diagram. We then rotate our wrist around the axis, right, represented by this velocity arrow. And then we try to rotate our wrist until we find a position in which it is natural to curl our fingers towards the electric field E. And if you do that, what you'll realize is you end up with your wrist rotated to the point where your thumb is pointing directly down into the page. Because when you do that, then with your fingers pointing to the left and the thumb down, the fingers curl very naturally towards the positive direction for the electric field, as I've shown it to you here in the figure. All that means, because your thumb is pointing downward, is that we are talking about a direction into the page or in the minus k hat direction if I want to be formal about it. The beautiful thing, though, is that that is exactly the direction of the magnetic field. So at least in our guess here, we've managed to find the right vector product to give us the correct direction. Let's now consider the magnitude of the vector that we're getting. Well, the magnitude of V is, of course, just V. The magnitude of the electric field is this quantity. So let me combine quantities in my numerator. So I have V from the velocity times lambda is in the numerator. I then have my denominator here, 2 pi r epsilon naught. So there's 2 pi r epsilon naught. And I'm left, of course, the only remaining term is my direction, the minus k hat direction. All right. Now, the next thing we then have to figure out is what is this v times lambda? What does this actually represent? So the first way to get a handle on that is to think about dimensional analysis. If I do v times lambda, right? If I think about the units on that, velocity is in meters per second. Lambda, on the other hand, right, is in coulombs per meter. So I see then, through the cancellations of the meters, that the units, the dimensions on this are going to be coulombs per second. And the beautiful thing about that, of course, is that that is current. So it looks like this product is going to give me something like current in the numerator divided by 2 pi r, and that is wonderful because it looks then like this V cross E guess that I'm working towards actually is giving me something very closely related to the magnetic field, which has current in the numerator and 2 pi r in the denominator. Now, what I've given you so far is just a dimensional analysis, but this is very promising. So let's now be a little bit more formal, a little bit more specific about it. If we think about our wire here, it's a long, narrow wire. And my wire, I'm going to consider a length of my wire L. And that wire, of course, is going to have a certain cross-sectional area A that I'll indicate to you there. And if I think about the meaning of lambda, right, this charge per unit length, that, of course, is the total charge on my chunk of wire divided by its length L. And the total charge, because remember, I want to get this in terms of things that I can relate to densities and current densities. The total charge there is equal to the total charge density rho times the volume divided by the length of my wire. And the volume of my wire, of course, is nothing other than the area of the wire times its length. And so I'm dividing by length. So what I learn is that the charge per unit length of this wire is just the charge per unit volume rho times the area A. Now that turns out to be a very important fact, because my next maneuver is going to be to notice then that that means that V times lambda will equal V times rho times A, because lambda is rho A. But I like this combination because I know that V times rho is the same thing as current density J. Rho V is how we usually write it, is actually current density J. Then I multiply by the cross-sectional area of my wire, and that is nothing other than the current I. So this actually, the dimensional analysis checks out for us. So now I think we can put things together. So what we've just learned from all of this, so what we see then is that when we did V cross E, what we really got when we did that was this V lambda, which we've just now proved is I. That gave me I over 2 pi r epsilon naught times minus k hat. So for this particular situation, when I do V cross E, I get something that is almost exactly equal to the magnetic field. The only difference is that the magnetic field result has a mu naught on top. Well, I can get a mu naught on top pretty easily. What I would do is I would take my actual magnetic field, B, which has the mu naught on top, and to reproduce this result so that I can write an equality, I have to divide by mu naught, which gets rid of the mu naught that lives in the magnetic field formula. So I divide that out, but I also needed an epsilon naught in the denominator, so I'll have an extra factor of epsilon naught mu naught. Perfect. So I can turn this around now. Now I know that the magnetic field for this case is given by epsilon naught mu naught times the velocity v of the wire crossed with the electric field from the wire. Now, what I want you to notice is my goal here. My goal was to get the magnetic field for this one case where I know the answer into a form of what I'm expecting to hold true in general, some sum over charges of velocities crossed with something. And here we see that we have, some constants, velocities crossed with something, and this something is the electric field. And I know how to write that in terms of a sum over my charges. So let's try that. We're getting B closer to what must be its general form. So epsilon naught mu naught times V cross, and if I write down the formula for E, you remember in Cartesian form it's sum on I, Qi, location R minus Ri, divided by, it's like a point charge, 4 pi epsilon naught, and then it's R cubed on the bottom to make the overall R squared dependence, R minus Ri cubed. Now let's see how we're doing. This is starting to look a whole lot like, in fact, what we were hoping. I've got a sum, I've got charges, a velocity, actually a particular kind of multiplication, a cross product. So let's continue to get it into this general form. So this would equal, well, a few things I can see I can do immediately. The epsilon naughts cancel out, which is nice because then my formula for the magnetic field only involves this magnetic constant mu. Now remember, the general form I was expecting was going to be a sum over I of Qi, each charge, times its own velocity v. So I can pull this v in to the sum. Again, remember, cross products, as long as you don't switch the order of any two vectors, cross products act like regular products. They're associative and distributive, so you can move them in and out of your summations at will. So I'm going to bring this into the sum next to the q. Then there's cross product after the v. And then what it's crossed with is everything else. I had to put mu naught on top, and then I have all of these remaining factors. So that will give me mu naught on top. The other factor on top, there's q, but I've already copied that over here. There's just then r minus ri divided by, then I've got 4 pi in the denominator. The epsilon naught was canceled out previously. R minus Ri cubed. So this relationship is true for the wire, right? This works for the wire. Now, here's the logic. Compare this to what we expected in general. The general form we expect is sum on I, Qi, Vi. Oh, this was a velocity vector, of course, when I carried it down. Vi crossed or multiplied by something. This is the expected general form. So the logic says, well, how can these two both be true? How can this be the explicit general form and this be what works in the case of the wire? for those two things to actually work out, it would be very unusual for this to actually happen unless what I've written for you here is the general form. Just in this particular wire case, everyone happened to have the same velocity. So they all happen to be making contributions with the same v. But if they were making different contributions or traveling at different velocities, like I would expect in the general case, what would I expect? I would expect to get exactly this form, except instead of just this generic v that everyone has, each individual velocity should appear. So that would be our best guess. So our final guess, and it's a very highly educated guess, and it's been confirmed in experiments over and over again. So it's confirmed empirically. So this is actually true, is that the magnetic field can indeed, at any location R, be computed by summing over the product of the charges, this QI VI, crossed, and notice now I'm using the velocity of each individual particle. If they're different for the different particles, that would be a V sub I, not just a generic V. Cross then with the Cartesian factor, mu naught R minus Ri over the magnitude cubed of these quantities, R minus Ri cubed, sum over I. That's one form for the law. This is the Cartesian form. You also, of course, have the trig option, which would be sum on I QI VI crossed with, and then you would just write it the same way we usually write our trig forms. There's going to be mu naught. This then would become R hat when you divide by one of these powers. So you would have R hat to from the location I divided by the distance to charge I quantity squared. So those are several forms now for the Biot-Savart law, right? This is for the case of either Cartesian or a trig form. So put parentheses here so we see how the parentheses work. Right, so this is Cartesian. This is trig. Now, the result I've just given you here for Biot-Savart is in the case where we have individual point charges. Of course, we would love to divide up a current-carrying wire or other object into a series of chunks and to convert these into integrals. So this is the discrete case. There's also, of course, the continuous case. Now, you'll recall the way we do the continuous case we described in quite a bit of detail in the previous lecture. I'll just remind you here a little bit on the side, a little side note. I want you to remember that we can always make the replacement sum on I QI VI. We learned we could replace that either with an integral over J dV, right? Or with an integral, that's one choice, or as an integral of I dl. And I should be a little careful here, of course. dv is not a vector, right? That's a volume. So d capital V, right? The vector nature comes from J, or if you're in a wire, it comes from the direction of the wire segments L. So I have these two replacements that I can make. You can take either Cartesian form or trig form, either form that you might want to use, and you can convert them either into volume form or wire form. So for instance, I might want to take the wire form. Oh, we should be careful. We went a little bit too quickly. Notice when I copied down my form for the magnetic field, when I carried out mu and the trig form, I neglected the factor of 4 pi in the denominator. So there's a 4 pi there, and there's of course a corresponding 4 pi here, so that then when I write my Biot-Savart law, for instance, in trig form for a wire, it would appear then where the sum becomes this integral. So I would have integral then of a factor, which is a constant factor, mu naught on 4 pi. So there's a mu naught on 4 pi. Here, let me clear that off here. Mu naught over 4 pi times the integral then of what's left over is QV is going to turn into IDL cross then with my trig form. So it's going to be IDL vector cross with r hat divided by r squared. Or another option, of course, would be to use perhaps Cartesian form in the volume integral. You actually have 4 different combinations you could try. It's kind of up to you. But the other form like that would be, again, I'd have my mu naught over 4 pi. Then my summation is going to become the volume integral, because I want to do a volume integral over j. If you want to be very pedantic, you would write the 3 integral signs. Right? And then the QV becomes the j dv, and that gets cross product with my factors, which I factored out, and my then Cartesian form, which would give me something like j cross r minus r prime. I'll be integrating over r prime divided by r minus r prime dv prime. So let me just remember this here was my little bubble thinking about how to turn these into continuous integrals. And then this is my final result for the JV form, or in this case for the IDL form. And all of these then are various variants of the famous Biot-Savart law that we can use to calculate magnetic fields given a set of charges moving with various velocities, as I've indicated to you here, in either Cartesian or trig form. Or you can think of it as a current-carrying wire, and you could do this in Cartesian or trig, or a volume distribution of currents J, which again you could do here as I've written it in Cartesian, or you could do it in trig.